Hi everybody, Dario Fresio here from fresioelectronics.com, and today I wanted to talk about the top 10 PCB design mistakes I made and also other designers make when designing for EMC and signal integrity. So the first design mistake that we're going to talk about is not choosing the appropriate stack up for the board. And what do we mean by that? Like in this case, you can see that this board is a 2-layers board and it has a signal on the top and signal on the bottom. So the scenario that we have is this one here, where we have a signal trace on the top layer, and then we have on the bottom layer another signal trace. But what happens in this case? What happens is that we have then electric fields, which are, like in this case, contaminating each other, also the magnetic fields. So the signal in here are really compromising each other. But that is not all, because also when we talk about the signals, we are talking about basically voltage. Okay, so if we are talking about voltage, then the voltage is defined as the difference between two potentials. If we have only one potential here, so where is the other potential? And the problem there is that then the fields are in here trying to find this potential for the reference. So the problem is really that by only thinking about one potential of the signal is going to be compromised itself. So what we would like to have is not to have this scenario here where the fields are just spreading from one trace to the other one and then they contaminate each other. But what we would like to have is a scenario like this, where we have the signal which has electric fields find a containment in here. So the field in here, they find the reference to establish the signal. So the difference between the two potentials. In this case, we will have, suppose that this is a signal of 3.3 volts. Then we will have 3.3 volts in here on the signal trace. And then this one will be the reference. So we will have a difference of voltage in here, which is exactly our signal. So you see that when you have the other case, how are you going to establish this voltage, which is in fact the signal? It becomes tough, because then the field will try to establish this voltage either when you route to the ground into traces, but then this means that the fields will extend until they find in here the reference. So let's take a simple case. This net in here now. Where is he going to find this reference? We don't know. In this case, I can see that in here there is a signal trace. So then, in order to establish the same condition like in here, where the electric field is basically coupling to the return reference plane, he will have to spread around, like in this case, until he finds the trace. And then, this is the scenario, because we have in here the signal on the bottom trace, which is then trying to establish the fields in the reference, which in this case, the reference signal is this ground IR 2110. So you can imagine that then the fields will start to spread in this direction until they can couple to this ground trace in there. Why is this a problem? The problem is that then these fields are not contained. You can see that in here the fields are contained and they're only spreading a little bit more around in here where there is no plane nearby. But this case in here is really when this plane is far from the signal trace. So when you choose a stack up where this distance is very high, because if you choose a stack up where this return reference plane is very close to the signal trace, then most of the fields are going to couple to this return reference plane. So most of the electric fields are going to couple with this plane in here. Going back to this point there. So what happens in this case is that now all these signals are basically in this situation where we have a spreading of the fields. And guess what? When we're doing the EMC test, what we're measuring is exactly that. So we're measuring how high are these fields and how much are going to interfere other devices and how much they're going to compromise the functioning of other devices. So you can see that from this stack up, we basically have no chance whatsoever of passing EMC tests, because the fields in here will be so spread around trying to find this return reference plane that they will couple to wherever they find the place. So this scenario here is really what we want to avoid, because also you see that we not only have the blue traces in here on the bottom trace, but we also have the other traces which are on the top, and the same will happen with them. So the same will happen that we have signal on the top and signal on the bottom contaminating each other, and this really will create, first of all, really high problems in terms of EMC, because it will create EMI. So it will create electromagnetic interferences that will spread around in the environment. And then we will have also signal integrity issues. Why we will have signal integrity issues? Because really you can see that the signals, if we define them as the difference between two potentials, really the signals in here are going to be both compromised because the reference for the potential is not controlled. So we really have no idea how this reference is going to be established and is going to create these problems. So when choosing the stack up, you always have to think in terms of fields. I know that many project stakeholders, they will tell you, choose the cheapest possible stack up. Okay, this is great. We have to choose the cheapest possible stack up, but at this point we are compromising the proper functioning of the board because really we have no chance of passing EMC with something like this. For how much I would like to make it pass with two-layer board, we cannot make it pass with two-layer boards because the field will be all over. So this is very important. When we are thinking about passing EMC, we have to think about the fields. How are the fields contained and how are the fields spreading around? Also, why is this the case? Not just because of the fields, but also this is called return or reference plane because of the return current. So the return part of the name is because of the current. We have to think about in terms of current. So let's take this signal here. So the signal has to go to the load, but then here it doesn't sync. So the ground here, this ground connection here is not a sink for the current, but the signal has to go. Also, it has to come back to the signal source. So when we're thinking about the signal, we cannot think about it just one way, but we have to think about also how the signal returns back to the source. So here we're using this simplification where we have only the power port, but really we have to think about this connection. So we have to connect this point in our mind. I think that most of the problems comes from this simplification here because we are really thinking about this part where the signal goes, but then we're not thinking about how the signal goes back. But still, the signal has been generated from this point, so it has to go and then come back in this point. And these points, so all the grounds, which these are called ground. But then we have to think about this, which is the return reference plane. So the return reference plane is called because it's used from the return current, but also from the voltage. So from the return current because of the loop. So we have this loop in here where the signal goes, reaches the load, and then it comes back. So not only the signal goes, but it has to come back to the source. So this is the part of the return. Now the part of reference. Why do we call it reference? Because the signal, in order to call it signals, we need to have a voltage. So the voltage definition is that we have a difference between two potentials. So potential, which is this part of the potential, but also the reference. So the voltage is this one here. When we talk about the signal, we're basically talking about how the voltage, so how the potential between this point and this point changes along this tracing here. So this means that the voltage is really the monitoring on how the potential in here changes from this point to this point. And this means that we are checking the voltage here, checking the difference of potential between this point in here, and checking the difference between the potential in here and in here. And then this means that we have this case in here. So this is the signal. The signal goes from the source to the load, and it propagates in this way. So suppose that we have 0 volts, and suppose that in here, when the signal is high, we have 3.3 volts. So the signal is propagating between the dielectric. So the signal really propagates as electrical magnetic field between the dielectric, and this propagation happens at the speed of light within the dielectric. And this means that we will have one point where the signal will be 0, so where the signal didn't reach yet at this point, and then we will have the other point where the signal will be already 3.3 volts. But in between, what we have is the signal wavefront, and this will depend on the signal rise time of the signal. So the time that it takes the signal to go from 0 to high level logic. So what does this mean for us? This means for us that when the signal is propagating through the PCB, so through the dielectric of the board, then we will have following this signal wavefront, so where the voltage changes from 0 to 3.3 volts in this case, then we will have also an establishment of this displacement current. This displacement current is possible because we have a changing electric field, which is this point in here, the signal wavefront, and this is the same that happens when we have a capacitor. So if you think about how the capacitor can conduct the current at AC. In reality, there is no conduction of current between the dielectric. Like in this case, there is no really current going through. But what happens is that the dielectric has some bound charges inside. So these bound charges, they are polarized as the electric field changes. So when the electric field is changing in this point, then the charges within the dielectric are then changing orientation and orienting themselves following the change in the electric field. And when this happens, it looks like there is a flow of current. But what really changes is the polarization of the charges within the dielectric. And this looks like a current, but in reality, it's not a current. It's just a change of the polarization of the dielectric, but we still call it displacement current. So these come from the Maxwell equations, and this is what has been called the displacement current, and is what happens also inside the capacitor. So inside the capacitor, there is no real conduction of current. So there is not a current going between one plate, the dielectric, and the other plate. But what is really changing is this displacement of the dielectric, which looks like there is a current going through. But this is what makes possible the signal propagation as well in this scenario. So what happens is that we will have then a signal forward current, which is the one that you see in the top trace. So this red trace that you see in here is the same as the trace that you see here. So what happens is that we will have this yellow part in here, which is the forward current. Then we will have the displacement current, and then we will have the return current. But this happens as the signal is propagating. So where there is the signal wavefront, we will have a displacement current in here. So this displacement current is what is closing the loop that we mentioned before, which we saw here. So the loop during the propagation is not just when the signal reaches the load and then it comes back and goes back to the source. But really this is happening instantaneously. As the signal is propagating, is always establishing this loop. So as the signal goes forward, it always establishes this loop. So as the signal goes forward, is always establishing this loop until it reaches the load, and then the loop is established, and this is what we are going to have. But this really it's happening instantaneously. So we always have this current loop, which is closing and going back to the source. And this is what we can see in here. So the signal here is really going source and going back through the inductance and the capacitance between the signal trace and the return reference plane, and then it goes back. So as the signal propagates, the signal current, which is the one here on the top, and the return current, together with the displacement current, they form this loop which allows for the signal propagation. So next time that you are choosing a stack-up, always think in terms of, first of all, fields. So how the fields are being established. So how is the voltage, so the difference between the two potentials, potential of the signal and reference potential, how is this voltage established? And is it consistent along the whole length of a trace? Because if it's not, then we have a problem within the voltage, which is the signal. So then, of course, we will have some signal integrity issues. So then the question is, what happens when we don't have the return reference plane? When we don't have the return reference plane, then we will have these fields. We don't really know where they're going to couple to. And the problem is that when we don't know where the fields they're going to couple to, then they're going to choose parasitic loops. And these parasitic loops are exactly what they're going to establish these loops in here. And these loops in here is what they're going to create electromagnetic issues. So when choosing the stack-up, I always think in terms of fields and in terms of return current. So how is the current going back to the source? And the best way that we can do that is by choosing a return reference plane. So what we want to have is a full plane. Like in this case, when we have a signal on the top, then we want to have adjacent return reference plane in here. Okay, so how to choose then when we have more layers? When we have more layers, the best way is always to think in terms of signal trace and then return reference plane. So always you want to build it in this way. And why is important to build it in this way? Because of what we said before. If we don't have this case, then the fields that we start to contaminate each other, like we saw in this case. So we really want to choose a scenario where the signal trace has always the return reference planes adjacent to it. Now, when we increase the layer count, then what happens is that, for example, now this is a 4-layer stack-up. So we have signal on the top, then on layer 2 we have return reference plane, then we have in here the dielectric, then we have again the return reference plane, which is giving the reference and the return also for the signal trace on the bottom. Now let's see how does it look like when we have a 6-layer board. When we have a 6-layer board, what we can do is, first of all, keep a little bit of distance between these signal traces, because we don't want that these electric fields are going to couple with each other. So we want to have quite some distance between this signal trace and signal trace. But at the same time, we want to have this signal trace. So this signal trace on layer 4 as close as possible to layer 5, where we have the return reference plane. And the same we want to do with layer 6. So layer 6, we want to be as close as possible to their return reference plane on layer 5. So we can do that because of the skin effect. So the current in here is not going to occupy the whole plane, but it's only going to occupy one side of the plane. So the other side of the plane can be used from the other signal trace. Now, of course, we want to be careful with what type of signal we're using, but usually this is the case when we have faster signals. When we have some faster signals, then the signal is not going to use the whole plane, but it's only going to use one side of the plane. So when this is the case, then we can use a 6-layer stack up like in this way, where we have signal on the top trace, then we have in layer 2, we have the return reference plane, and then layer 3, we have another signal trace. And the same we can do in here, where we have a signal trace, and then we have return reference plane and signal trace. So this part in here will be isolated from this side because we are using some distance so that the fields are not going to interfere with each other. But for that to happen, we need to have layer 5 and layer 4 as close as possible to each other, and the same with layer 2 and layer 3. And of course, we want to have everything symmetrical, so if one side of the board is within one way, the other side of the board, for manufacturing purposes, we want to have it ideally the same. Okay, now let's go to problem number 2. So what is problem number 2? Problem number 2 is having the traces very close to each other. So we talked already about the signal crosstalk. Like in this case, we have this signal which are very close to each other. So this means that the electric fields, so these fringe fields in here, are going to couple with each other. So the fields of this signal there will couple to this signal here. And then what happens is that then we will have the signal compromised. So this will be a signal integrity issue. But also, how can this be an EMC issue? So let's see how easily this can become an EMC issue. Because if we have the signal here, which is coupling to the USB in this way, then we will have that this signal is going all the way to the connector. So can couple in here, and then from here it can couple to the cable, and then from the cable you can find the path where to propagate. And then this is what is going to cause an EMC failure. So this is what can cause the failure of your test. So when placing the traces, we really want to keep some distance between the traces. So if the width of the distance is 1, then we wanted to have this distance here, at least 2 or 3. And we can see that the same happens in here between this PD13 and PD14. So the signals here are very close to each other. So what will happen is that when we have the transition of the fields from the 0 volts to the signal level voltage, then if this is very sharp, this transition time is very sharp, then we're going to have some issues there. Because this is going to contain some high harmonic content. So the sharpest is the transition between this voltage level to this voltage level, the more energy there is in these harmonics. And this is what is going to create then these coupling issues, because we will have the fields which will couple one trace to the other in this case. So this is the second mistake. Keep the traces with as much distance as possible. So this is the case when they are not differential pair. When they are differential pair, we want to measure what is the coupling that we have so that we can control it. But when we're talking about signal that they are not a differential pair, then we want to keep as much distance as possible. So we want to keep this distance between the traces as much as we can. Use the space of the board. Of course, you want to route the traces as short as possible. But anyways, think in terms of the space that the fields will occupy. So you want to have quite some space in here so that these fringe fields, they don't couple with each other. Now, the next problem that we are going to talk about is reducing the parasitic effect from routing. So what do we mean by that? By that we mean reducing, for example, like in this case, this path in here. So this path in here is that when we're connecting components, like in this case, we want to keep as short as possible these traces. Why do we want to do that? Because these traces in here, they have a certain inductance. So if these are the capacitors which are providing the coupling or the bulk capacitance for the microcontroller, then what happens is that we will have in here certain inductance, and this is going to have an impact on the impedance of the power delivery system, or the power delivery network, as you want to call it. And this is exactly why you will read from certain application notes where they tell you place the coupling capacitors as close as possible to the microcontroller or to the pin that they are serving, because of the inductance. Because the inductance in there is going to increase the impedance of the power delivery system. And this is going to create a problem when you have either a microcontroller or a processor or an FPGA, which requires some instantaneous sharp energy. So when it's requiring this energy in peaks, then this is going to create a problem, because then you will have these fast switching signals which sees the impedance in here. So get rid of as much trace as possible, keep them as short as possible. The same goes when you're doing the connection with the grounds. So if you're connecting with the ground, you want to keep these traces as short as possible. The same because of the inductance. So when you have this type of connections, exactly these type of connections are inductive. So when the signal current is flowing back to the source, then we see this impedance here. And then if we have an impedance here, and then we have a current which is flowing through this impedance, what we're going to have is a voltage. And this voltage here is noise. So depending how sensitive is your system, then this is going to create some issues. So this type of connection, we want to keep them as short as possible as we can. In certain cases, we can also use vias in pad, but this, of course, is going to cost us some extra money. But anyways, in most of the boards, you can just route this as close as possible, and you're going to just be fine. Now let's go to problem number 4, which is large current loop size. So this is a problem that we can see quite often in switching regulators, and this is going to create, of course, EMC issues. So we want to keep the loops as small as possible. To show you a loop, I will show you now this example here. So what do we mean with large loops? So what's important for us is this switching node. The switching node in here is where we have this inductor, then the feedback to control the output, and the output capacitor. And then in here, we go back to the source. So this is the loop that we are talking about. Okay, so what happens is that usually these points, the inductor and the capacitor, are placed far from each other. And what happens is that then this switching loop is large, and then the magnetic fields from this switching loop is going to create some issues. So what we want to do is place as close as possible the inductor here and the capacitors here, so that this loop is very short. And this we're going to do it in the layout. We're not going to do it, of course, in the schematic. We can just point it out. We can say place it as close as possible, but then this is going to be implemented in the layout. So in the layout, we want to place the inductor and the capacitor as close as possible to each other, but also as close to this pin, so that we can create this small loop. And why this is important? This is important because this is a switching loop. So this switching loop means that in here we're going to have signals that are going to transition very fast. When they're transitioning very fast, like we already mentioned, we're going to have this scenario here where we have a high energy harmonic content. And this is what is going to create the EMI troubles, because we want to have them as contained as possible. So the fields, they need to be as contained as possible there. Remember that if we don't contain these fields, then these fields are going to be picked up by the instruments in the EMC lab. And then this is going to result in a failure of your test. Okay, so the next one is going to be adding protection and/or filtering for each input and output. So what do we mean by that? By that we mean, like in this case, we have a USB cable, which is coming from the outside environment. So the cable is coming in here and then reaches this USB connector. And then these traces reach inside the board and reach this circuit in here, which then propagates and goes to the other microcontroller there. So what's the problem here? The problem here is that we have this long cable. We don't know how long this is in this case. This can be also meters long. So we have a longer cable. And when we have this longer cable, what happens is that any signal that is coming can couple to this cable. And then from this cable, it goes inside our board. So what we want to have in here is we want to have some sort of protection right at the input and output of the board. So before the signals enter the board, ideally we want to filter these signals. The case, for example, when we have a USB, in here we want to have, first of all, ESD protections, so that we can protect the signals coming from the outside, so that we can revert as fast as possible the interference that is coming and coupling to the cable and then sneaking inside our board. For each point where we have some kind of out connection, then we want to have some sort of filtering for the signals, and we want to have also some kind of transient protection from the outside environment. So the same goes for this connector there. If we have in here a cable which is entering the board, then we want to filter as fast as possible. Before the signal even enters the board, we want to filter it and get rid of the interferences as fast as possible. But the same can happen when we have only output signals. So if we have output signal as well, we want to filter them before they go out from the board. We don't want to place the filters here, because otherwise in here there can be still some coupling and then the signal goes out. So the filter has to be as close as possible to the connector, because in this way, if there is an interference inside, this will be get rid in here. If instead we place the filter too far from the connector, then the interference can still happen here and the filter is not useful anymore, because then at this point the interference is happening here after the filter, and then this sneaks out of the board, and then in here we will have the emissions. So place the filter as close as possible to the connectors. In this way we are filtering the signals that enter the board, but also the signals that goes out of the board. So this is something that you want to check when you have a layout. Check that each connection that goes out has some sort of filtering. Now this filtering can also happen outside of the board. So you might have it not to place inside the board, but then this is another case. Ideally you want to have it also included, and at least the footprints, you want to have them included inside your layout. And this goes to point number 6, which is separating grounds between digital ground and analog grounds. So why this is important? This is important because of what we discussed before, because the signal is not really propagating first on the trace and then reaching the load and going back, like we discussed in the other example where we had the signal propagating this way, then reaching the load and then going back to the source. This is not really the case. In fact, we said that the signal, as is propagating, is always closing the loop. So the loop is always closed because of this intercapacitance that there is between the signal trace and the return reference plane. And this is possible because of the displacement current. So if we create a separation of the planes, what is going to happen? So I'm going to show you what is going to happen with this simulation, where we have a signal trace, which is going from one side to the other side of the board, and then we have a split in the middle of the plane. So imagine that this is the signal on the top, and then you have this plane on the bottom there, which is cut, which has a cut in the middle. So what is going to happen? And to show you what is going to happen, we're going to use this simulation. So you can see that the signal really reaches this point and then it starts to spread between these two planes. So between the cuts in the plane. So these colored arrows that you see are really the fields that are spreading between these two planes, the plane 1 and plane 2. So you can see that this is going to spread the fields in one direction and the other one. So what is going to happen is that these hit some resonance of the cavity. So the cavity is basically the space between this plane and this plane. And then this is going to create other issues in terms of signal integrity, EMC, because depending on the frequency in here, we will have some propagation of the signal outside of the board. And this is exactly what we want to avoid. Take this example here where the signal on the red trace is transitioning from this point to this point. So at each point in time, you will have this condition where the signal current can flow back to the source because there is this return reference plane. But then what happens when it reaches this point? Then the signal will feel kind of lost because it doesn't have anymore this path where it can return back to the source. So here then the fields start to spread around, like we just show in this case, where we have this field that start to spread around, they've lost, and they don't know anymore how to return back to the source. So in here the signal will feel lost and then it will start to spread around wherever it finds its way through. So we don't want to have signal that cross cuts like in this way, they don't cross splits in planes because the return reference plane and because of the reference of what we discussed before, because then these fields are going to spread around, and we will not have this scenario where the voltage between the signal trace and the return reference plane is well established. But also, what is the possible nightmare in here? If you have these two sides of the planes, which are connected one side to one cable and the other side from the other cable, then what is going to happen is that we are going to create this kind of condition. So the condition in here, we are going to have one side of the plane, which is connected to maybe one side of the cables, and the other side of the plane, which is connected to the other cables. And then in here, you have a voltage difference. You can see here, this is a voltage difference. And what you just created in here is a dipole antenna. And then this is what is going to happen as well when you have a split between analog section and digital section. This is exactly what you want to avoid. So you don't want to create a section where you have analog and digital section with the planes. So the only separation that you want to have in this board is to have analog components and routing on one side and digital components on the other side. But this plane, this green plane in here, it should be the same plane. It should be the same return reference plane. So without cutting it out. So without creating splits, without creating cuts, because also what happens is then you start to route, like in this case, over the splits, and then these create other problem. Like we showcased in here in the simulation where we have basically the fields that go through this cavity here. So inside this cavity, you see in here, the signal is already propagating through the cavity. And then it's going to reach the other side of the systems, and then it can create also emissions. Never cut the return reference plane. Okay, let's go to problem number 8, which is strategically placing components, in particular crystals, decoupling capacitors, filters, protection, and terminations. So we are going to take the case of the crystal. Why we want to have the crystal oscillator as close as possible to the pins that they are feeding. Again, because of the point that we mentioned before, when we have a clock signal, we have something similar like this digital signal here. Of course, it's not going to be really as sharp as that, so it's going to have some kind of slope, but this still means that we have these high energy harmonic contents. So let me show you what does this mean. In here we have the oscillator, and look how far this oscillator is from the neck that it is serving. So imagine now if you have a square signal in here that is trying to reach this point. This is a very sharp digital signal which is trying to reach this point. These harmonics now, that they will have also a long way in here where they could potentially couple to other signals, and then they can disturb either all the signals, or they can reach also the power net, and then from the power net then they can also propagate outside of the board. So this is one of the most common issues. Why? Because usually what happens is that then the clock signals are going close to the power traces. Then the clock signal couples with the power traces, and then the power traces, of course, they reach the power supply, and then from the power supplies, they conduct through the cables, and then the conductive emission test is going to be failed. So when you're routing, especially clock signals, you want to route them as close as possible to the pin that they're serving. What can happen in here, as I pointed out, these traces are very long, and this square signal can couple to other traces. It can even couple to this trace and then can reach here, and then from there it can reach this point, but this is also a cable, and then from the cable it can just propagate out. So from just placing this crystal oscillator, first of all close to the output and then far from the point which is feeding, then you can have the signal in here coupling to this USB, and then from the USB is going to travel to the power delivery network. And this means that your conductive emission test is going to fail, or possibly even the radiated emission test. So place the components strategically. So think about what is the purpose of the components and where should it be placed. So the coupling capacitors, like we mentioned, they have to be as close as possible to the pin that they are feeding. The same goes for the crystals. And for protection, like we mentioned, we want to have the protection as close as possible to input and output, so that we are actually protecting our circuit and that we are actually protecting other circuits when the signals are going out of the board. So now let's go to problem number 9, which is controlled impedance traces. So not choosing controlled impedance traces. So why is this a problem? This is a problem because, like we mentioned before, the signal propagates from the source to the load. But during this signal propagation, the signal is expecting to have a certain impedance, because if we have a mismatch of the impedance, then the signal will reflect. So what happens when the impedance changes? The impedance is the ratio between the signal and the current at any point in time. So this means that if the ratio between the signal and the current changes, the impedance changes. But the same applies if the impedance changes, because if the signal is fixed, but then the impedance changes, then the current changes. Or if the current is fixed and the impedance changes, then also the signal changes. But you can see that this will create some issues for us, because we want to have the signal as clean as possible. That's why we call it signal integrity, because this has to be as clean as we can possibly keep it, from source to destination. So not choosing an impedance and not keeping it throughout the whole length of the trace will cause some mismatches between the impedances, and this will create the reflection of the signal. So let me show you a point where we can have this issue. This issue, we can have it in here, where we have a signal which is going in this direction, and then here you see a split. So then what happens in this split? Then the signal is going to see that this point is 50 ohm. So this is 50 ohm. What's the impedance in this point? Because now the signal will come to this point and we see that in here the impedance has changed. You will have to decide what to do in this plate. And then here is where we create the reflection. So the signal will come to this point, and then some part of it will reflect back and some part of it will propagate one side and the other part will propagate on the other side. But the signal that you are going to measure is going to be compromised, because now is not anymore this signal here, but is a portion of the signal. And then you have to count the reflection there, because then, like we said, one portion of the signal will reflect back, and this reflection, you don't know what is going to cause, because if in here there are all the signal, so here we keep propagating back, then it reaches this point, then in here there can be some crosstalk. So then the signal spread also in this trace, and then it's just going to create a big mess in our circuit. And this can result either in signal integrity and or EMC issues. So don't create impedance discontinuities. Use a controlled impedance trace. So typically for signal traces, we use the 50 ohm, because most of the driver use the source impedance as a 50 ohm or the input impedance as a 50 ohm. So that there's a match between the source and the load. And you want to keep this the same throughout the whole propagation of the signal. So if, for example, you choose all the signals like USB, LVDS, PCI Express, and all these more sophisticated signals, you want to then make sure that the impedance is correct. And this you typically find it either in the datasheet of the manufacturer of the IC. You can Google it and you can find it immediately what the impedance that you should use for the signal traces. And then to calculate what is going to be the width based on the impedance. So for instance, with Altium, you can do it from the layer stack manager. Go to the layer stack manager and then you find impedance, and then based on the stack up that you have, you can add an impedance profile, and this will tell you already what's the impedance of your signal traces. So if you have in here, you want to have an impedance of 50 ohm, and then it's going to tell you, okay, if you want to have an impedance of 50 ohm, then you should have this width of the traces, because your top trace, which is the top traces in here, is having a reference with the layer 2, which is also reported there, and this should be the width of the trace that you should use. So it's simple as that. You can see in here, this is 50 ohm, the profile for a 50 ohm impedance. And then in here, you need to have another impedance, then you can calculate it in here. So this is calculated with Symbior. Symbior is a software that we use many times for doing electromagnetic and signal integrity simulations, but it's also integrated here. So this is good because it tells already what you should use if you want to have a certain impedance profile. So if you want to have a characteristic impedance of this net in here of 50 ohm, then you should use this width of the trace. Then let's go to problem number 10. Problem number 10 is creating antenna-like structures. What do we mean by that? Maybe we can choose another layer here. Antenna-like structures are, for example, can be something like this, where we have this part in here, which is a plane, this part in here, which is another plane, but then we have this small signal trace, which is connecting the 2 points. The problem with these two is that in here, we're going to have a voltage. So we're going to have a voltage here, and then we're going to have a voltage here. But these two voltages, we have in here a certain impedance that goes with the trace. So the voltage that you have in here is different than the voltage that you have in here. And this can create the scenario that we discussed before, where you have this voltage on one side, voltage on the other side. Now, what happens when, like in this case, the board has not the correct stack up and the layout is not properly done? Then you have a signal going into this tracing here, but this one can couple to this tracing there. Then you can have here the signal source, one point in here with certain voltage. And then if this one is having the same condition, like in this point, where you have a certain voltage on one side, a certain voltage on the other side, you just created this dipole antenna, and this will propagate. So you don't want to have this kind of scenarios where you're creating antenna-like structures. So antenna-like structures are structures like this one here, for example, where you have a separation between two planes connected by a thin signal trace, or where you have like large signal traces which are creating loops. When there is a huge current loop, there is also a magnetic loop, and this magnetic loop is also an antenna itself. So you don't want to create antenna-like structure with loops or with this kind of geometries. So be very careful about the geometries that you use. You want to keep in mind always to keep the impedance as uniform as possible. So here you have a certain impedance, then in here you have a certain impedance, and here you have a certain impedance. So this is not going to create a nice situation for us, because you have three different impedances, and you don't want to create this type of geometries where you have these dipole antenna structures.